Have you ever paused your favorite video game right at the perfect moment? Or sent a selfie halfway across the world in just seconds? What you are actually seeing is not real. It is not a picture, or sounds, or colors. Seriously. Underneath all that, it is just billions and billions of incredibly simple electric switches shouting either on or off. Your computer brain isn't reading data. It's just listening to the world's most chaotic stadium cheer, organized into code. How does this pure lightning chaos create this? In this video, you will finally understand the mystery hidden right in your pocket. You are going to learn how absolutely everything in your digital life, from cat videos to online bank accounts, is made entirely of tiny flickering lights. You will understand exactly why computers can only count to 2, but are somehow the smartest things we have ever built. And we are going to explore the secret, mind-bending recipe that makes your phone feel less like a machine and more like a trusted friend. Let us get to the value. Let us start with the absolute basics. What is a computer? It is not a person. It is not magic. It is a machine. And like most useful machines, it needs power. If you want a fan to turn, you push a button, right? You let electricity flow. If you want it to stop, you push the button again. You break the flow. That is the entire secret. Computers do not speak English. They do not understand your photos. They are built on billions of microscopic components that act exactly like your light switches. These components are called transistors. If electricity flows through them, they are in one state. If the flow stops, they are in another state. That is it. Imagine a single light bulb. It can represent one simple piece of information: the light is on. If you have 2 light bulbs, you have 4 possible combinations: both off, first on, second off, first off, second on, or both on. If you have billions of these on-off components, you can represent almost anything. But we needed a language to write it all down. That language is binary. And it is not a secret spy code. It is just math. We decided to use the number 0 to represent off, meaning no electricity, and the number 1 to represent on, meaning electricity is flowing. Your computer has billions of these zeros and ones, floating like a digital ocean. We organize them. Think about text. How does a processor, which only understands electric current, read the letter A? We created a simple dictionary. We assigned the specific, tiny number 65 to A. When the processor sees the binary pattern 01000001, which is 65 in binary, it simply displays the shape of A on your screen. It is the same for colors. Every color you see on your screen is just a specific blend of 3 lights: red, green, and blue. We assign a binary number from 0 to 255 for the intensity of each color. A bright yellow pixel might have the instruction: max out red, max out green, keep blue turned off. In binary code, that is just 3 specific numbers sent to that pixel. This next part is wild. How do billions of static lights move things? Let us use an analogy. Imagine you are standing outside at night in front of a giant skyscraper. It is completely dark. But thousands of windows can have their lights turned either on or off. Now, imagine a specialized light architect is inside the building. He has a sheet of paper with thousands of tiny boxes, and a perfect recipe. Step 1 might say, turn on lights in row 5, columns 10, 11, and 12. Step 2 says, row 6, columns 9 and 13. Step 3 says, well, you get it. The architect reads this very specific list of on-off instructions. As he works, you, standing far back, suddenly see a giant, glowing face smile at you from the building. It does not look like a computer code. It looks like a picture. Now, imagine this architect is superpowered and can read 60 new recipe lists every single second. If step 60 shows the face's eye slightly closed, and step 100 shows it completely closed, then that giant glowing face is not just static. You, the audience, are now watching a cartoon blink. That light architect is your processor. The recipe list is the program or video game code. And the giant building is your screen. The processor is just flickering microscopic windows, organized into a moving picture that tricks your brain into seeing life. But this is where it gets truly amazing. We are not just displaying pictures. We are calculating. How do these on-off switches do math? How does a pile of binary lights decide which way your game character should dodge? This is the secret engine. They do it with logic gates. This is the real brain work. A single light switch, a transistor, is just a switch. But we can build clever pathways combining them. A logic gate acts exactly like a tiny filter. Think of a water faucet that needs two separate handles to be turned on simultaneously before any water flows. If you only turn handle A, nothing. Handle B, nothing. You must turn A and B. That is a logic gate. Specifically, it is an AND gate. In binary terms, if you give it two ones, electricity on both, it outputs a single one. Another gate might be an OR gate. Imagine a gate where water flows if either faucet handle A or handle B is turned. We can even build a NOT gate, which flips the signal. If you put a 1 in, electricity flowing, the NOT gate cleverly outputs a 0, which stops the current. By layering billions of these incredibly simple AND, OR, and NOT decisions inside the processor, we can create incredibly complex logical math. The processor is not thinking. It is just cascading a tiny river of electricity through a massive, smart obstacle course that results in your game character moving exactly when you tell it to. So, now we have the language, binary, and the tools, logic gates. The last step is the routine. How does a processor actually do its work? It follows a continuous loop, millions or even billions of times a second. It is called the fetch, decode, execute cycle. Think of it like a professional chef. First, the chef gets an instruction card from the recipe rack. This is fetch. The processor reaches out to your computer's memory, the RAM, and gets the next binary instruction. Second, the chef has to read the card. It might say, Step 4, chop the onions. The chef decodes the instruction, understanding what needs to be done. The processor breaks down the binary pattern into, aha, this pattern means I need to add 2 numbers. Finally, the chef actually picks up the knife and chops. This is execute. The processor activates the precise logic gates needed to perform the task, like channeling electricity to the AND gates that handle addition. As soon as that calculation is finished, the chef is already fetching instruction card number 5. This loop never stops as long as your computer is running. Your processor is not reading data. It is just dancing in the electrical rain, flickering its switches in a complex, predetermined pattern that tricks you into seeing another reality. I want you to try a practical experiment today to make this science feel real. Do not worry, this is safe. Go home and find the lowest quality, smallest JPEG image file you have. Right-click on it, go to Open With, and choose Text Edit on Mac or Notepad on Windows. You will not see a picture. You will see a giant wall of messy, random-looking text and symbols. What you are looking at is the binary code for that photo, just represented in our alphabet. It is that messy recipe list. That entire block of chaos is what your processor just decoded and then light architected into a picture. You are looking at the digital paint itself. Try it. If you loved finally understanding the invisible magic hiding in your tech, hit that subscribe button right now. We post videos every single week to explain the invisible science and secret engineering that runs our modern world. Subscribing tells the algorithm that you want brain-boosting educational content in your feed, and it helps our community grow. Before you go, leave a comment below. If you could give your computer brain one logic gate filter for your own brain, which one would it be? For me, it would definitely be a NOT gate for that third cup of coffee. Let me know yours. Thanks so much for watching. Do you want to know how Wi-Fi signals actually travel through solid walls? Click the video on your screen right now to find out. See you over there.